All right, so let's look at how we can determine coordination modes and once again and confirm an inorganic structure synthesis using IR. So the story for this goes that we have some starting material. So there's a starting reagent that we have, and as well as some bipyridine. Those are mixed, and then we end up with two proposed structures, structure number 3 and structure number 4. And how we then are going to use the IR spectra to elucidate which structure did indeed form. Now, the easiest way to look at this quite complex spectra is to first assign the peaks that are due to new Joule mole in which it was ran. So we're going to eliminate that peak, or these peaks, you can see from the starting material and the product are from new Joule, as well as this little peak in this doublet, so round about this area and the doublet can be eliminated for new Joule mole. Okay, the rest then we know is from these ones. Now we can start talking about how we'll be able to differentiate between these. So both of them have tin chloride bonds, so there's the chlorines there's some chlorines there. And both of them are going to have tin nitrogen bonds. So tin nitrogen, yes. So the only real difference, and this is essentially whether or not the ester group is coordinated or is free. So let me just clean that up. So we're looking for an ester group when it's coordinated, means it's in structure 3. And it would look similar to the starting reagent, because the starting reagent also has an ester group carbonyl that is, coordinated. So let's give them a color. So if they're coordinated like that, so meaning coordinated like that, then we'll highlight that color, and we shouldn't see a big shift in what we observe in the peak. Otherwise, if we see a shift, then we can assign it like that. Okay. So the two IR spectra that we're given the one with the starting material. And we know typically carbonyls are going to lie in the 2000 to 1500 per centimeter range. So in this general area here is what we're concerned with. And we see there are two peaks there. The one in the reagent is this one, and the one in the product is that one. Now, the important thing here is if you actually look at where they are, then the peak at the bottom is at 1713. The peak at the top is at 1651. So in other words, the bottom one, the product, gives a shift, and it gives a shift upwards of the spectrum. And that's normally associated with something decoordinating. So when a ligand coordinates, their peak normally shifts to a lower energy of excitation. So meaning that the product is something where the carbonyl is no longer linked to the structure. So this is actually, in fact, in this color. So it means peak or structure 4 is the structure that is most likely to have this because of that peak difference that we saw. Meaning that the peak moves from a coordination point, which would be lower in energy, to a free coordination site, which is higher in energy, shown from the carbonyl stretch. That allowed then the bipyridine to be a bidentate ligand. You might have also been tempted to look at the bipyridine stretch, and it's roundabout here, so I'll highlight it for you. So we would have looked at this stretch here to say, whether or not is the bipyridine only monodentately coordinated, or is it bidentately coordinated? And in the starting material, you can see there is no carbs tin nitrogen stretch. But in the product, what you get is you get this broad kind of peak. And the broad peak indicates that there is some sort of influence between the two nitrogens that couple the SN bond of the one and the SN bond of the other one. But you see it's a very loose argument. It's not very definitive, since both of them will have tin nitrogen vibrational bonds. The better one is to see what is the shift in the carbonyl from the reagent to the product. If there was no shift, then we would have had structure 3. Since there was a shift, we know there's structure 4. Okay, so that's how you can use your knowledge to know what a structure looks like ultimately. Okay, thank you for watching.